All right, now that we've defined general measures of quantum entropy, I would like to focus and discuss a specific and very interesting new measure of entropy that actually approaches its classical definition in the semi-classical limit, and that is the Ks entropy. So I would like to first start off with a discussion of the classical definition of Ks entropy, as it varies pretty significantly from the regular Bothman definition of entropy. So the Ks entropy or metric entropy was first defined when physicist Andrei Kolmogorov was trying to distinguish between systems that were only defined by ODEs that are completely deterministic compared to sort of stochastic differential equations. So given this, to define the Ks entropy of the system, we first examine some partition in phase space. And as the partition in phase space changes over some discrete time interval, there are many possible, for each trajectory within the partition, there are many possible different trajectories it can go because it's not completely defined because there's some stochastic element. So what we do is take the Shannon entropy over all trajectories within that partition, and that defines the Ks entropy for that one partition. Then to get the Ks entropy of the entire system, we take the Sapernium, so the greatest possible, the least upper bound of the Ks entropy for any given possible partition. So this is a very theoretical concept. It's not really something you could. It's not easily measurable in the lab, but it does tell us how random a system is, how predictable the system is, and sort of how much information we can get out of it. So that is defined. The Shannon entropy for the different probabilities is defined by this equation below. So as we can see, it's not as very clear how we would derive the quantum analog to this, because we can't really have phase space and partitions, and quantum phase space is quite odd. So we will just start off by looking at the Ks entropy for just some given initial starting point, which is defined by this. So some initial starting point with some regular Hamiltonian coupled to some weak noise, because that will come in later when we start coupling our quantum system to weak noise. So as you can see, the Ks entropy for it, where the dimension is Q over some particular dimension, is given by this equation, which can be rewritten as the Renier entropy. So the Ks entropy is actually the time rate of change of the Renier entropy, which is useful because the Renier entropy is actually defined in the quantum sense. So as we can see, this is the equation given for the Renier entropy of a single starting point, and then the Ks entropy is essentially the time evolution of the Renier entropy. And this the dy dt is actually can be thought of as a probability cloud. So given some initial starting point, all the infinite possibilities sort of expand in a cloud at some later time t. We can then take the expansion of that cloud, right, as that probability cloud expands in space. We can take the entropy of that, or the Ks entropy of that, and the variance of that cloud, and that will describe the Ks entropy for that initial starting condition. And in the final equation I described, it defines the variance of the cloud as the determinant of some 2x2 matrix, which is A sub t, and then that over T naught is just some initial starting point, so that is normalized at some initial starting condition. And then now that we've got it, so now that we sort of understand the Ks entropy is really talking about how much the probability cloud of some initial trajectory happens over time, we can start working and start describing the Ks entropy. And to do this, we actually start off with the Renier entropy, because we know it should be the time rate of change of the Renier entropy. And using second order time dependent perturbation theory, we consider a system where we have some, quantum state or some quantum evolution that is then instantaneously coupled to a auxiliary heat bath. So like most quantum experiments happen in place, when, almost absolute zero temperatures. So this example, this was defined because we can kind of go from what we know is a relatively low and not as chaotic state into a more chaotic state, and really will help us understand more of the sort of open quantum systems and how decoherence happens. So as we can see, I obviously won't be able to go through the entire derivation, but given the Renier entropy, we can define some matrix, matrix A, which is similar to the matrix A that we described earlier, which is taking where x of t in this equation is the coupling to the heat bath, and phi naught is the initial pure state. So as the as the so the coupling grows, as the coupling to the auxiliary heat bath grows and affects the pure state more, we can see the probability cloud changes and expands, and that is reflected in this equation where we have some one plus epsilon squared tau. That's not really important. It's essentially telling us that the expansion and the coupling to the heat bath over the wave function defines the Ks entropy of the system, which is also convergent to the classical definition in the semi-classical limit. So essentially, if we take a limit as h bar goes to 0, we see that the equation converges to its classical definition, which is super useful because via the Pessin relation, we know that the Ks entropy should just be the sum of all positive Lyapunov exponents. So if we were to try and define some quantum Lyapunov exponent, it would also have to equal the Ks entropy of the system, which we have defined in this case. But there are a few problems with this definition, and I would say the largest problem would be the time scale. When solving for this problem, we assume that epsilon would be small, relatively small. But if you set epsilon to 0, then this equation doesn't really make any sense. So we have to choose a time frame where that's not so long that it would be completely random and completely classical, or and we can't choose it so small that epsilon would be small enough to make the equation not understandable. So the authors of the paper that I was referencing was able to define some time frame, and it actually seems like this issue with timescale is reflective of any quantum Lyapunov exponent. So in some capacity, even though the timescale seems weird, it actually has actually an expected thing to happen. So moving on, this is useful and informative because it will help us define some quantum Lyapunov exponent, but it'll also help us to understand and define more connected thermodynamic quantities, and some that might actually be measurable in real life.